Hello, this is Noah Hutson and Luke Williams here to present to you the fish tank project that we worked on over the winter quarter of Engineering 121. The purpose of this system is to regulate salinity and temperature within a fish tank system. This system here is not very practical for use in the real world, but it's very practical for learning in the student life. How it works in general, it measures salinity through a conductivity sensor and checks against variables that we set if it is within certain control limits. If it is not, then the salinity is corrected with DI and saltwater tanks. It then measures heat through a thermistor, which will be more thoroughly explained later. And then if the temperature is outside of the limit that we set, too low, we turn on the heater and the temperature is then corrected. This flowchart here explains it fairly well, the order in which things work in the system.
How the water system works. Shown by the blue arrows, that shows the current of the water, the direction it flows in. The pump brings the water down from the main fish tank and it flows it through the bottom right hand portion of it, shown there. The three-way valve, which is not pictured, we use the open and close setting. The open setting allows it to flow through and circulate through the system, and the closed setting allows it to drain through the overflow. The reservoirs, there and there. The one on the left hand side contains the DI water, the one on the right hand side contains the salty water. The solenoid valves, there and there, are powered by an electrical current. When that current is turned on, it opens the valves up, which releases the water, and it is pulled down by gravity into the main fish tank.
The electrical system works. The first question you might have is, where does the power come from? Well, the power comes from mostly a 12-volt power source, AC to DC converter, that's mounted on the wall, and the smaller currents come from Arduino pins, and the Arduino can actually be powered by the 12-volt source. And the voltage and current is from where? Well, usually it is sent from the Arduino, at least the controlled current is, and then just the power itself comes from the 12-volt. To what? It can go anywhere from transistor relay circuits to power the conductivity sensor to turn on an LED to notify us that the heater is on. Electrical control from smaller to larger current is usually achieved through transistors and relays. A transistor basically allows a small amount of current to regulate a larger amount of current, and then a relay basically expands that from that current to a much larger amount of current, and those circuits are used in both solenoids and the heater. The measurement system on our fish tank is at first a conductivity sensor to measure salinity, made of ultra-high molecular weight polyethylene with two stainless steel rods put into it. The water passes through the conductivity sensor and electricity is sent through the water. As the water salt content increases, its resistance decreases. Thus, we can measure through calibration and analog input the change in salinity and the exact amount of salinity in the water. 1023 is a very important number because we use an 8-bit system, and that's our conversion factor from analog to voltage. The conversions from analog to percent, here's one. You can see right here that it's a power equation. That would say the E, 2.718, to this number times the analog times this gives us our percent. Our thermistor is actually a resistor. You can see it sort of in the system, the upper wire. Basically, as the heat increases in the system, the resistance increases in the system, and thus we can calibrate and figure out exactly the change in temperature. The analog input has the same conversion factor, 1023, unlike an RTD, which would be much different because you're using 1.1 volts instead of 5. But for both the thermistor and conductivity sensor, you use 5 volts. The conversions here are very linear and very much more simple than the conductivity sensor because the thermistor is much easier to work with.
How the system controls salinity and heat. First off, we have the DI tank, which is filled with deionized water, which is 0% NaCl. We have the salty tank, which is filled with 1% NaCl. We have the solenoid valves there, which, powered on by the electrical current, bring water into the fish tank from the tanks. The heater pictured there in the relay circuits. The heater is powered by the relay circuits, and whenever it's turned on, it heats up the water inside the main fish tank valve.
The code overview, your first question might be, well, what does the code do? Essentially, the code is system control. It basically calculates the conversions, it reads the salinity, it reads the temperature, and then it reacts. It calculates the necessary conversions through sets of equations. Shown here are a couple of them, and basically just goes through, and there's several equations that calculate the different things that are necessary in the code. The code has separate parts. First, you have to initialize. You have to open up all your pins. You have to make sure that it is in the right bit. You have to initialize everything that you need to initialize, declare your variables and such. Then next, you're going to read. This is AR analog read 1. This would be for the conductivity sensor. There's an AR2, which is for the thermistor, and it actually reads and then checks. It checks to see if it is within the control limits that we set. And then if it is not, the code reacts. In this instance, if the water was too salty, the DI valve would be opened for this amount of time, T open, which is found here through this equation, X being the mass of water and FR3 being the flow rate of the solenoid, and then it is turned off so that you don't have an infinite overflow of water.
Troubleshooting. From day one, we had many problems, such as on the first day we split wood building the tank. Programming was trouble every day. Getting the coding right was definitely not easy. Wiring was also not easy, as we burned out all our LEDs and several times had the wiring completely wrong. On the day of the testing, we spilled water on our whole circuit, which caused us to fry our LCD, and we had to clean that up, and it took probably 2 to 3 hours worth of overtime to get that. And on one day walking to class, our LCD completely froze, which caused the top hand part of the screen to not work, causing the numbers not to even show. And those are just a few of the problems.
Though this coding and system could have been much better, it was an excellent learning experience, and I really enjoyed it and hope to continue learning. Thank you very much.